Section 3.2, polynomial functions and their graphs. So we just finished quadratic functions and their graphs. Now we're going to work on polynomial functions and their graphs. So upon completion of this section, I should have the understanding and skills to determine the degree, the coefficients, the constant term, the leading term, and leading coefficient of a polynomial. Demonstrate the difference between continuous and not continuous graphs. Demonstrate the difference between smooth and non-smooth graphs. Determine the end behavior of a polynomial. Find zeros of a polynomial. Use end behavior, zeros, and test points to graph a polynomial, labeling important features. Find the local extrema of a polynomial. Determine the multiplicity of zeros. Use degree, multiplicity of zeros, and leading coefficient to write a polynomial function. And then use all of the above information to sketch a graph of a polynomial. So let's start with making sure we remember what a polynomial function is. So a polynomial function of degree n is a function that's in this form. And notice it's a coefficient and then x to the end, another coefficient, and x to the n, another coefficient, x to the n minus 1, all the way down till we have a coefficient times x and then a constant. So, and it's where n is a non-negative integer. So notice that the exponents must be non-negative. Non-negative. Why don't we just say positive? Well, because 0 is okay also. Exponents must be non-negative and they must be integers. So that means they can't be 0. They can be 0. They can't be negative. And they can't be decimals or fractions. Unless they can't be decimals or fractions when they're in their simplest form. Okay, and then notice that it says that a sub n cannot be 0. So that first coefficient can't be 0, otherwise it wouldn't be degree n anymore. Now the numbers a sub 0, a sub 1, a sub 2, a sub n, those are all called the coefficients of the polynomial. So those are all of the numbers in front of the variable and also the constant. So the a sub 0 is the constant coefficient, or you might often hear it called the constant term. The number a sub n is the coefficient of the highest power, so then that is called the leading coefficient, and the whole term is called the leading term. So let's highlight this in a different color and give it its name. So a sub n, that is the leading coefficient. And then the entire expression here is called the leading term. And just as a quick reminder that we should also remind ourselves that terms in an algebraic expression are separated by addition or subtraction. And then factors are things that are multiplied times something else. Okay, so the degree of a term, make sure we make this distinction. The degree of an individual term is the exponent of the variable in that term. Or if you have more than one variable, then you add the exponents of all the variables together. But the degree of a polynomial, so that's of your entire expression, is the highest degree of any of the terms. So let's try to make sense of some of this vocabulary. So fill in the blanks. What is the degree of this polynomial? Well, the degree will be whatever the highest exponent is that we have. Correct. So the degree is 5. Now it says, what are the coefficients in order? So my first coefficient is a -4. My next coefficient is a -3. The next one is a 2. The next one, the one that's in front of the negative x here, that's going to be a -1. And then remember, this a sub 0, a sub 0, a sub 1, a sub 2, all the way up to a sub n. Those are all called the coefficients of the polynomial. So 10 is its own coefficient. It's a constant term, but if you're asked to list the coefficients, then you also include that. Then we just said the constant term is 10. Now the leading term has to be the entire expression that has the highest exponent. So the leading term is -4x to the 5th. But if you just want to talk about the leading coefficient, so leading term is the entire expression that's first, the entire term that's first, highest degree. And then the leading coefficient is just the coefficient of that term. So it would, in this case, it would just be the -4. Okay, so some facts about the graphs of polynomial functions. All polynomial functions have graphs that are considered continuous. So what do we mean by that? They're continuous if there are no breaks, no jumps, and no holes. Then that's considered continuous. It's considered smooth if there are no corners or sharp turns. So polynomial functions are continuous, they are also smooth. So now we want to draw some examples of graphs that meet these criteria. So let's start with A. It has to be a graph that is not continuous at x equals a. So I could draw pretty much anything that's got a hole in it. So let's say here's A right here. I could have a graph that right here has a hole and goes like this direction. And then here we got something that looks like this. So notice I have a jump in my graph at x equals a. Or I could do something like this. This could be filled in. Or I could have something like this, where it's just some kind of, almost, like a polynomial, some kind of crazy curve, but right at A, there's a hole, and then this curve keeps on doing something crazy. So neither of those graphs would be what we call continuous at A. Now they want me to draw some graphs that are not smooth at x equals A. So really anything that's got a corner or a sharp turn at A. So like here's A. I could do something that goes, and then I go, oh, darn it. Let me fix that. It goes, and then goes like that. And that's at x equals A. So I've got a sharp corner right there. Or let's say A is right here. If I have a graph that goes like that. Man, I didn't draw very well at 8, so let me just do this. So there's A. So notice how there's like the sharp corner there. Or even, how about a absolute value function that has a sharp corner right there? All of those would be considered not smooth at A. This one wants me to draw a graph that would be considered smooth and continuous everywhere. So honestly, it's just any kind of like, that would be considered smooth and continuous everywhere. No breaks, no jumps, no holes, no corners, no turns. No sharp turns, no corners. Okay. Let's see here. So now, just to a quick refresher on notation. When we write this x arrow infinity, that would mean that x goes to infinity. That is, x increases without bound. And if we write x goes to negative infinity, that's exactly what that means. X goes to negative infinity, that means it decreases without bound. So one of the things we're going to talk about right now is end behavior of a polynomial. So the end behavior of a polynomial of this general form is determined by the degree n and the sign of the leading coefficient, and it's as indicated as follows. So there's two, first of all, remember there's two criteria here. So the degree and then the sign of the leading coefficient. Those two criteria. So if the degree is odd, oh, we need to address something here. Do I have room down here? I do. Okay. Even function and odd function is different from saying even degree or odd degree. So remember, an even function is one that is symmetric with respect to the y-axis. An odd function is one that's symmetric with respect to the origin. So those are more about location, but now we're talking about odd degree or even degree. So odd degree just means that the highest exponent is an odd number. So if your polynomial has as its highest exponent an odd number, and then this one is telling me, so this is odd degree, but leading coefficient positive. So if it's an odd degree, leading coefficient positive, it goes up as it goes to the right, and it goes down as it goes to the left. So as x goes towards infinity, y goes towards infinity. As x goes towards negative infinity, y goes towards negative infinity. Now, if it's odd degree and the leading coefficient is negative, then as x goes towards infinity, your y becomes more and more negative, so it goes towards negative infinity. And then as x goes towards negative infinity, your y becomes more and more positive, so it goes towards infinity. I'll give you a little strategy here in just a minute. Now, if you have an even degree and your leading coefficient is positive, then your end behavior will be that your tails both go up. So as x goes towards negative infinity, y goes towards infinity. As x goes towards infinity, y goes towards infinity. And if you have an even degree and your leading coefficient is negative, then your tails are both going to end up in the down direction. So typically the way I remember this is if my leading coefficient is positive, I know the right end behavior will be up. Now, if it's even degree, then both sides have to go in the same direction. If it's odd degree, then your ends go in different directions. So again, if it's a positive coefficient, I know the end behavior on the right will always be positive. If it's a negative coefficient, then the end behavior on the left will always be negative. And then if it is a odd degree, then your ends go in opposite directions. If it's an even degree, then your ends go in the same direction. All right, so in the next video, we'll start practicing this.